Hello, my name is Colin. If you've never been to this channel, I'm an architect at Juniper Networks, and if you have been to this channel, thank you for coming back, and apologies for my output in 2022. It has been a very busy year, and after I completed and uploaded my Apstra Lab series, lots of work responsibilities, life stuff, I haven't been able to do as many of these as I like to do, and I am rather excited to be getting back into it. Today, we are going to be talking about MC lag, and this is going to dovetail into the Campus Fabric series that I've been hinting at in the last couple videos. The concepts that we're going to talk about today are going to be germane to the campus discussion because we are going to be talking about ESI lag. We are going to be talking about why you would use ESI lag and how you can migrate a legacy architecture like MC lag into an ESI lag design. We aren't going to be using the Campus Fabric lab though. I haven't decided if this is going to be a part of that series strictly or if it'll have its own little playlist on YouTube. I'll figure it out later. For now, let's get into this video. Quick walkthrough of the lab environment. There's a few things worth noting from the jump. It's a very simple access distribution kind of pretend core just because that's where the L3 is. Keep in mind the L3 is here. I'm going to do two different ESI lag migration videos, one where the MC lag pair is just doing L2 and one where the MC lag pair is doing L3, where we'll move this configuration down here and we'll configure VERP on our MC lag devices. I'll be doing a test to begin with. It's a ping from client 1 to client 3. Just trust me that these all work. I'm not going to open them all up and ping through all of them. Also, in this initial state, these devices are not configured for MC lag. So these AE interfaces do not exist. And this link that interconnects these two devices here at the distribution layer is there, but it is disabled. So it is not a data path. And that's because I want to show what this looks like without MC lag as a use case for why you might use MC lag. We're running spanning tree here, so you know one of these links is going to be blocked. Let's start by talking about what MC lag actually is. MC lag it's kind of a loophole. I mentioned that in the video notes that I had on the other view. LACP, the Link Aggregation Control Protocol, is defined by the IEEE 802.3 AD standard. And if you ever have trouble remembering that, configuring LACP on Juniper boxes will help you remember because you literally have to type in 802.3 AD in the config. The Link Aggregation Control Protocol is defined by the standard, deals with the signaling both between switches that are running a aggregate and how that control plane functions on those switches themselves. What it doesn't do is it doesn't say that that control plane has to exist on a single device. And because of that loophole, a lot of network equipment manufacturers, Juniper included, have created a proprietary protocol that allows the synchronization of that LACP control plane between two different devices. This is also why you can't mix and match multi-vendor MC lag devices. The ICCP, the Inter-Chassis Control Protocol that Juniper uses for MC lag, is not going to be compatible with whatever it is that Cisco uses. They call it MLAG, not MC lag, or what Arista uses or anybody else. That's two of the elements of MC lag. LACP, obviously, the ICCP for the control plane synchronization of LACP. I also have ICL here. ICL is just the inter-chassis link. It's a data plane. If you've got traffic that lands on one host that needs to be forwarded out of the other, you need to have a data path, much like if you were doing clustered firewalls for that traffic to travel over. And that's this link that is currently disabled in our existing design. Now, just for sanity's sake, I'll show you that we can ping from client 1 in the bottom left to client 3 in the upper left. That works fine. Our path in this case is going to be like this because I know, at least assuming that this continues to be deterministic, that this link is being blocked right now by spanning tree. And we can show that by getting onto these switches and saying, and these are the two at the distribution layer. That's how I have this grouped: show spanning tree interfaces, and sure enough, we've got a blocked interface here. All right, that's all expected. Now, quick you and me time. I'm going to show you how to configure MC lag. Now, obviously, the title of this video is Death to MC lag, so this is just being done for context. The social contract that you have with me right now is that you're not going to use this video to configure MC lag in a production environment and just leave it there. You can do this in a lab, but I don't want to train you how to use MC lag because the whole purpose is don't use it. So watch the rest of the video, take from it what you will. Build an MC lag lab if you want, but don't put it in production. If you want to do that, go watch somebody else's video. I don't want to be a part of MC lag in production environments. All right, moving along. Back to the lab. Rather than actually walking you step by step through the config, which, I've got hiding another screen, but you don't get it. I'm going to load configs. I've saved the configs. I'm going to preload them. And then I'll walk you through what those differences are. So we'll go to this pair first, config, load, override, MC lag, commit and quit. And we'll jump to here and do the same. So I don't have to throw this video out like I did for the last one. I'm not going to forget to resume this link. This link carries the control plane synchronization. I was already recording this video a few minutes ago, and I forgot to resume this link, and I was wondering why my pings were broken. Well, it's because MC lag was broken. We'll get to the show commands again at the end, but I am going to make sure that this is working now. It says that it's in progress, and it's established in up. We also have some BFD elements here. I'll talk about that as well. It says unknown, but this should be working at this point. There we go. And we'll make sure that our ping is working. This video has to be re-recorded here if I hit enter and this doesn't work. So fingers crossed. There we go. Thank goodness. Re-records suck. So MC lag is up and functioning, and these AE interfaces are up. Basically, what you see on the screen is now what is in place. Let's walk through what we've done. How is MC lag working? And we'll start that discussion by looking at the protocol itself, the ICCP. So show protocols ICCP. When you're building your inter-chassis control protocol, you're going to define a local IP address. Typically, this is going to be a loopback. I'm not doing that here for the sake of simplicity, because if it is a loopback, then I need to have either a IGP running between these hosts, or I need to have static routes set up. And in this case, I'm just using an interface IP. Not technically, it's an IRB, but not the loopback. So we define our local IP address, then we define our peer. And this is where MC lag starts to get really fun. We have elements of the MC lag configuration that need to be globally matching. We have ones that need to be locally matching, and then globally unique. We have things that need to be globally unique. And every time I configure MC lag, even after years of doing it, I still to this day use a cheat sheet, because it's a huge pain in the butt to try to remember all this stuff. All of the values that you see here obviously need to match aside from the local and peer IP. We have session establishment hold time for the ICCP link itself. This redundancy group ID, it does need to match a value that is within the interface configuration for MC lag, but it can be any integer. For my part, I just make it 1. This concept is similar to cluster redundancy groups. I've never built MC lag even with 1,000 VLANs or interfaces where I have multiple redundancy groups. It's always just the same one. And then we've got BFD configuration. Now, something to take into account here is there's a lot more config that could go into just about every component of the config I'm going to show you. This is the minimum amount of configuration that's required because I don't like configuring MC lag, so I'm not leaning into more work. The ICCP interface config goes first. Next, we'll talk about the ICL. This is the inter-chassis link that connects the two hosts. It is that link here that I showed you in the middle. Normally, you would have an aggregate that has multiple members. I'm in a virtual lab, so I'm not doing that. If you have a chassis, it's a good idea to aggregate those physical links across multiple cards. So if you lose a card, the link degrades, but it doesn't go down. We also recommend using the same link for the ICCP and ICL. They don't have to be the same link. Certainly, if you're looking at firewall clusters, we have a discrete connection for that control plane synchronization, and then there's a data link, a fabric link is what we call it. In the case of MC-Lag, we say make them the same. There are some considerations as to why you do that. Again, best practice guide, right? The ICL is not too complicated. It's just an aggregate interface. Oh, and I forgot to mention, since we're using aggregates, make sure that you have a few of these defined, or else your AE interfaces aren't going to work. Show interfaces. I'm using AE0 for the sync here across XE000. Nothing much to it. There's no strict MC lag configuration on this link. It is not an aggregate that is split between the two devices. It's an aggregate that connects the two devices. So we're not going to see the MCAE configuration here under aggregated ether options like we'll see in the actual MC lag interfaces. This is a simple aggregate, and this aggregate carries VLANs that are associated with the MC lag interfaces, as well as the VLAN that is being used for the ICCP. That VLAN, in my case, it's VLAN 100, has this IP address for the IRB. And I can actually show that to you here. I can do show VLANs. You'll see the ICCP interface right here at the top. You'll see that it's associated with IRB 100. And if I do show interfaces IRB.100, there you go. I do note here that the ICL doesn't support some protocols. That's why the spanning tree configuration on this has been removed. If we do this, you'll see that it's not there anymore. I did have it set up as RSTP interface all. You can actually do that and then say RSTP interface and then the interface like AE0 for the ICL and then disable if you want to do it that way. Oftentimes you'll have folks that are continuing to run spanning tree across an MC-Lag L2 pair. That's good, sure, fine, but the MC-Lag pair itself isn't going to be participating in spanning tree. Not that ICL link. It appears to the rest of the network as a single logical device, so we don't have to worry about these bridge calculations that RSTP is doing. In my case, I just deleted it from the config. Next step, let's look at what the aggregate interfaces actually look like. So we have two. We have AE1 and AE2. There's a lot of config that's the same as a normal aggregate, but there's definitely additive configuration as well. So we'll just look at AE1 and AE2 together. And the reason we're going to do that is because, like I mentioned before, there are components of the config that need to be matching, globally matching, unique, but locally matching. It's a whole thing. So we've got the same LACP active configuration here under the aggregate, but we also have this system ID and admin key that have been added as well. Now these need to match across the two members, but they do need to be unique across the different MCAE interfaces. Try to keep up. I hate this so much. We also have this additional stanza here for MCAE. We have an MCAE ID, and you can see that that needs to be the same across the members, but it needs to be unique between each aggregate. When you're coming up with these values, wherever possible, match them to your AE number. You can see that these are all ones, and down here, these are all twos. It's just so much easier to keep track of. Even if I'm not using AE0, I would probably still start at AE1 just so that I can have that value here to keep things in order. Now this redundancy group, that doesn't matter. That can be the same everywhere, but it does need to match. Actually, is that true? No, actually, I don't think it even needs to match. Oh, I hate MC lag. Oy. It does need to match here on this box, and this needs to match the value that you have in your ICCP configuration, but nothing more. Chassis ID, this is very similar to a cluster. The two options are 0 and 1. You're just giving it a unique node number. And then there's a mode. I'm not going to get into active standby. I'm running an active-active. That means I've got active data plane on each box. And then since I'm in an active-active mode, I need to have status control defined. What this will do is influence the behavior if we get into a split brain scenario. And then below that, we've got the same unit configuration that we would have on any other aggregate. Now, you might think that you're done, but you're not done. There are two more things that you need to configure. You need to configure switch options, and you need to define a service ID. That can be a rando number. This service ID is used to spawn a service that is used to synchronize certain protocols across the ICCP. I don't know that there's any special considerations for what that number is. I don't think it has to match between. Does it? Maybe it does. I don't think so. I don't know. Make them the same. It won't care. And we also need to define multi-chassis protection. This is a requirement. You should look at this. And again, we have that kind of peer relationship where the multi-chassis protection is configured with the IP address of the other device. And you define an interface. And in this case, that's AE0. That is it. Confusing, huh? And one of the reasons I want to walk you through this is because there is a tendency, I think, to look at EVPN-VXLAN and ESI lag as a replacement for MC lag and think, oh, that's too complicated. I don't think it's that much more complicated than MC lag. I think there's more people that are familiar with MC lag, but I don't think that from a side-by-side configuration standpoint that it is that much more complicated. And certainly, as we get into this section of why it sucks, the ability to troubleshoot MC lag when it breaks is just atrocious. Was it really easier than EVPN-VXLAN? I'll let you decide as we get into the next video where I actually show the migration. I don't think so. There's a consistency check that actually is intended to help you make sure that your settings are right. I'm going to go ahead and pause and turn that on because right now it is not on. The way you would look at it is you would come here, you say multi-chassis. You might think that there's an enormous amount of information that I can use this initial command to get. No, I can type in MC lag and I can do configuration consistency. Those are the only options. And then I've got some specific things, but if I hit enter, it'll just show me all of these other sub options. I hit enter, that's not turned on. So through the magic of video editing, I'll enable that right now and I'll show you what it does and then I'll show you why it sucks. So hold on for a moment, please. Fading back in. All right, the consistency check has been turned on. If you want to do that in your own implementation, you can do it under the multi-chassis configuration. You'll see that I now have this consistency check enabled. We look at the consistency check here. We'll see that we have all pass values again. Great, no failures. However, let's take a look again. So what I've done is something naughty. I have changed the AE2, and then we're looking at AE1 interface here, the AE2 interface values for admin key and system ID to be identical. All right, so here we go. Hit the space bar again. We'll get down to AE2 and you'll see that these now match. That's a no-no. These are supposed to be the same across aggregates on the different boxes, but different between the aggregates themselves. And in this case, I've made them match between the aggregates themselves. All the consistency check is doing is it's checking to make sure that we have matching values between the peer and the local, and I'm sorry about the wraparound here, but it's not checking between the different interfaces themselves, which means that you could have an issue and the consistency check isn't going to catch it and things are going to act weird and it's going to look like everything's okay, but it's not. So I'm going to go ahead and just undo that. And commit and quit. Why else? Well, I do mention dark magic being used to troubleshoot. It's not too evil. It's just there's not a lot of information available. If you've got the consistency check off or even on, as we've seen, it's not the end-all be-all to tell you exactly what's broken. And outside of that, like I'd mentioned, if you look at the multi-chassis show commands, it's only to view the consistency check. So there's no help there. We can do a show ICCP, and I think you might have detail here. It doesn't give you too much more information. You'll know if it's up or not. If it's up, but things are broken, what is this telling you? Not much. And we can also do a show LACP interfaces. And if we do detail or extensive, pardon me, we will see this value. So this might help us determine if we've got some information being mismatched, but it's LAC-P. I mean, this isn't specific to multi-chassis lag. It's just giving us information that we did define during the configuration of MC lag. Outside of that, you're going to be looking at Ethernet switching tables. You're going to be looking at ARP tables if you're running L3. It's just there's not a lot that you can work with there. And the other two that I highlight here, scale. If you're using this with chassis or using with a VC, you do have a scale consideration. It might seem like it's a universal scale consideration. How many members can I have in my virtual chassis? How many cards can I put into this chassis? You'll see this when we do ESI lag. You've got a lot more flexibility, a lot more horizontal scale, because we've got a protocol that is distributing our control plane and basically programming other switches. That's an N+1 situation. Now, there are upward limits that you probably want to stay underneath, but they far exceed the scale of a chassis or virtual chassis. And finally, what we mentioned at the jump, it's proprietary. That's it for this video. The next one, I'll show you the migration, and then we'll do an L3 migration as well to EVPN-VXLAN. We can do it in one commit. I don't know that that's going to be great for every use case, but I think it'll be hopefully compelling in this example. Thanks for watching. Thank you for coming back. If you're ready for more videos, so am I. I'm real excited to get into this lab, this campus lab that I've got. Have a great rest of your day, and hopefully I can get another one of these videos knocked out today. Take care.